From the moment we rise to the time we close our eyes, we are enveloped by a symphony of sounds. The gentle chirping of birds greets the dawn. The bustle of city life fills our days with a vibrant hum. Even in the stillness of night, the soft whisper of wind or the distant rumble of thunder reminds us of the constant presence of sound. But have you ever stopped to think about what sound truly is and how it travels to reach our ears? Sound is not an object but a form of energy. It's a wave that travels through different mediums, and our ears are finely tuned instruments designed to detect these waves. Imagine a pebble dropped into a still pond. The ripples that spread outward from the point of impact are analogous to the way sound travels. Sound is our connection to the world around us, an invisible force that shapes our experiences and interactions. By understanding the science behind sound, we unlock a deeper appreciation for the symphony of our universe. Sound in its simplest form is a mechanical wave. This means it requires a medium to travel. Unlike light or radio waves, which can travel through the vacuum of space, this medium can be a gas like the air we breathe, a liquid like water, or even a solid like the earth beneath our feet. Imagine speaking through a string-connected cup. Your voice, converted into vibrations, travels through the string, carrying your words to the other end. Here, the string acts as the medium for sound transmission. Without it, the sound cannot propagate. The absence of a medium means there is nothing for the sound waves to compress and expand. This is why in the vacuum of space, no one can hear you scream. At the heart of every sound lies a vibration, whether it's the plucking of a guitar string, the beating of a drum, or the rustling of leaves in the wind. Sound originates from the movement of objects. These vibrations create disturbances in the surrounding medium, setting off a chain reaction that we perceive as sound. Picture a bell being struck. The impact causes the bell to vibrate rapidly. These vibrations in turn cause the air molecules around the bell to vibrate as well. These vibrations propagate outwards, compressing and expanding the air molecules in a pattern of high pressure regions called compressions and low pressure regions called rarefactions. The back and forth movement of air molecule creates a wave that travels through the medium, carrying the sound energy with it until it reaches our ears. It is this pattern of compressions and rarefactions that our ears interpret as sound. Decoding sound, wavelength, frequency, and amplitude. Just like ocean waves have unique characteristics like height and frequency, sound waves also possess specific properties that determine how we perceive them. Three of the most fundamental properties of sound are wavelength, frequency, and amplitude. Wavelength refers to the distance between two consecutive compressions or rarefactions in a sound wave. Frequency, on the other hand, measures how many complete waves pass a given point in 1 second. It determines the pitch of a sound, with higher frequencies corresponding to higher pitched sounds and lower frequencies to lower pitched sounds. Amplitude, and the final piece of the puzzle, dictates the intensity or loudness of a sound. A larger amplitude corresponds to a louder sound, while a smaller amplitude results in a quieter sound. Understanding these three properties allows us to unravel the complexity of sound and how we experience it. A sonic journey through different mediums. While sound can travel through various mediums, it doesn't always do so at the same speed. The speed of sound is influenced by the density and elasticity of the medium through which it is traveling. In general, sound travels faster in solids than in liquids, and faster in liquids than in gases. This difference in speed is due to the arrangement of molecules in different states of matter. In solids, molecules are tightly packed, allowing vibrations to transfer energy quickly from one molecule to another. Liquids, with their more loosely bound molecules, conduct sound slower than solids, but faster than gases. Gases, with their widely spaced molecules, offer the least resistance to the movement of sound waves. This explains why a train approaching from afar can be heard sooner through the railroad tracks than through the air. The denser medium of the steel rails allows sound waves to travel faster, providing an early warning system. The dance of reflection and refraction. Just like light bouncing off a mirror, sound waves can also be reflected and refracted, leading to intriguing phenomena like echoes and the apparent change in sound intensity based on the time of day. Reflection of sound occurs when sound waves encounter a surface and bounce back. The classic example of this is an echo, where a sound wave bounces off a distant surface and returns to the listener with a delay. This delay is directly proportional to the distance between the sound source and the reflecting surface. Refraction, on the other hand, involves the bending of sound waves as they pass from one medium to another with different densities. This bending can cause sound to travel further or be focused in a particular direction. For instance, sound travels further at night because the cooler air near the ground is denser than the warmer air above, causing sound waves to refract downwards and travel closer to the ground. Understanding the reflection and refraction of sound is crucial in various fields, from designing concert halls with optimal acoustics to developing sonar technology for underwater navigation. It's a testament to the fascinating ways in which sound interacts with the world around us.